Hello, welcome to this video. On behalf of Tatsari, Francisco, and Manuel, we'll show you our transfer processes to final project. Now let's begin with a convective mass transfer problem as part of our chosen topic. I'll resume you the problem statement as well. At a paper industry factory, there's a treatment plant within. In order to clean the wastewater and use them for industrial purposes, there's an open pond with measures of 100 meters of length and 300 meters of height, where wastewater is diluted with chloride. As part of a regular water treatment procedure, considering a factory in a warm area, the air temperature is at 35 degrees Celsius and its atmospheric pressure is around 1 atmosphere. The bulk velocity will be of 8 meters per second and the liquid phase at the temperature of 20 degrees. The diffusive coefficient will be 1.3 x to the minus 5 squared centimeters per second. The standard condition at the gas phase got a kinematic viscosity of 0.2 squared centimeters per second and a diffusive constant of 0.092 squared centimeters per second. This is our collected data. As I previously mentioned, and the needed key element to solve the problem are those. Parting from a laminar flow, we have to check the required length to be considered as turbulent flow and also the average film gas transfer coefficient. At the right side, you can observe the diagram or chart of the process and how the yield is expected to be within the system. We can assume that our diffusivity is constant. That is a convective mass transfer problem as the topic mentioned it, and it's a one-dimension problem. There's a change of flow presented in the system as well. So, considering a Reynolds number of 2.x to the 5 as the minimum acceptable value to be considered as turbulent flow, we can apply the Reynolds number formula by isolating the length and substituting the Reynolds number value, turning the speed into centimeters per second. At the end of the position to be determined as turbulent flow will be of 50 centimeters. In order to find the film gas mass transfer coefficient, it must be by starting getting the Reynolds number formula and applying within the pond length to obtain a Reynolds number of 6.x to the minus x to the 6, which will be helpful to use it at the Sherwood number equation. So that can happen. The Schmidt number have to be gotten and simply by dividing the kinematic viscosity over the diffusive coefficient from the gas. The Schmidt number will be around 2.17. After that, we apply the Sherwood number formula regarding to a turbulent flow and we substitute the values that we found as well. Finally, the film gas transfer coefficient is obtained by the following formula below and it's substituted with all the gas phase data and the initial length of 100 meters that will be converted into centimeters with an arc of 82.06. Our final result will be of 1.53 x to the minus 5. The application field of this process can be used in the environmental area, fields development, petrochemistry, food and inorganic chemistry, and more. The most common process to be used with this method are gas absorption and liquid stripping, also in a distillation area as well. By concluding with the problem, as far as the length decreases, the Reynolds number will be increased as well. The yield of the wall of the flow will be moving faster, which is subjected to the decision of choosing the right Sherwood number equation. Depending on the flow, the chloride gas will be assuming as turbulent, and that's why we focus on it. Thank you for your attention and hope you're staying at home and following the right measures. Have a nice afternoon.